Recording in progress.
Hey Trinity.
Hey, how you doing? I
Doing
only
good.
have about like 10 minutes because I have to head out.
Mm-hmm.
But I do have like this one topic I was wondering if you could go over.
Yeah, let's do that. What's that topic that you wanted to go over?
So it's tertiary. It's basically like alcohol reactions. So it's like the SN1, SN2, those kinds of reactions. Just like mechanism wise,
Right,
like
right.
where to put carbocations, how to know like stereoselectivity, regioselectivity type of thing.
Right. Yeah, like SN1 reactions, SN2, with HCl acid. Let me see here.
Yeah. It says alcohols and strong acid. So there's tertiary, secondary, and primary. So I was just wondering about those.
Right, right. Okay. Let me show you that. And HX. Okay. And then you want us to go over like the SN1, SN2 reactions as well. Let me see here.
Yeah. Just a quick little review because I have an exam on Monday next week, so I just wanted to kind of like look over that a little bit.
Right. Okay. With alcohols. Okay. Let me share my screen.
Yeah. Great. Thank you.
Yep. Okay. So for this one right here, there's gonna be different types of alcohols you could have. You can have methyl alcohol, which is like CH3OH. So I'm gonna abbreviate that as
ROH.
CH3 or like ME, and then there's primary alcohol, and then there's secondary alcohol, there's tertiary alcohol, and there's a nucleophilic acid, HX, where X is a halogen like chlorine, bromine, or iodine.
Yeah.
And then there's a non-nucleophilic acid like h2so4 with heat, and that's gonna do like elimination reactions, E1 or E2, right? So now I'm gonna separate this chart into SN1, SN2 reactions. So here, let's say in SN1 reactions, there's a carbocation intermediate.
Okay.
Right? And carbocations have to be stable to exist. So those are going to be stable for like secondary and tertiary carbocations, because a methyl carbocation is very unstable. And then a primary carbocation, wait, no, actually this is a primary carbocation over here. Let's say CH3, methyl carbocation, is the least stable. And then this is a primary carbocation, and then this is going to be a secondary carbocation, and then this is a tertiary carbocation.
Okay.
Right. The more substituted the carbocation, the more stable it is. Right. So if you have an HX with a secondary or tertiary alcohol, you're going to do an SN1 reaction. Right. But if you have a primary alcohol, you're going to do a SN2 reaction. Right.
Yeah.
Specifically, like an unhindered, primary unhindered carbocation. I don't think Helix went over hindered carbocation with a concerted hydride shift, so we won't go over that. But I'll look through your notes, and then if you did go over it, I'll go over it with you tomorrow in the tomorrow's office hours, right?
I get what you're saying a little bit, the sterically hindered stuff. I understand. Like if there's too much surrounding it, then it's gonna like prevent basically.
Right. Like we don't want steric hindrance in SN2 reactions, so that's why in tertiary alcohols we can't do SN2 right there.
Yeah.
Right.
Yeah.
Okay. And then with heat, there's gonna be elimination reactions. So we can't do elimination reactions with methyl, but we can do E2 with the primary, and then we could do E1 with secondary and tertiary.
In E1. Okay. Yeah.
E1, right? Because E1 and SN1, they both go through a carbocation intermediate, and then carbocation intermediates can be stable in secondary or tertiary positions.
That makes sense, because the secondary and tertiary aren't those let me see, SN2, SN1, because I know, hold on, sorry, I'm blanking out. One reaction's faster than the other. The other requires the formation of cations, so that would be SN1.
SN1,
Okay.
and E1. They both go through the carbocation intermediate.
So those are slow
Right.
reaction,
Yep.
and then SN2 is fast reaction.
SN2 and E2.
Got it.
SN2 and E2, right.
And those form, which one forms double bonds again? E2 or the
E2,
eliminations?
yep, all the elimination reactions. The E reactions form double bonds, right? And here is the stability of double bonds. This is an unsubstituted double bond. This is a mono-substituted double bond. And there's going to be 3 di-substituted double bonds. There's cis, there's geminal, and there's trans. And then this is going to be tri, and this is tetra, right? But for the 3 di-substituted one, the geminal and cis are going to be the same stability. The trans is going to be more stable than a cis and geminal. And then the more substituted the alkene is, the more stable it's going to be.
Okay, so stability.
Right, this is the stability chart right here for alkene.
Stability is to the right, you said?
Yep, it increases from left to right. Yeah, because we see this alkene here on the right is tetra substituted because there's 4 R groups surrounding it. Whereas the one on the very left is unsubstituted, right? There's no R groups. It's surrounded by hydrogens only. It's the least stable because there's no R groups around it, right? Very similar to carbocation intermediate. Like the more R groups surrounding the carbocation, the more stable it's gonna be, right? Okay. So now let's go start with some practice problems over here. I'll give you a simple one to start off with. Let's say we have this alcohol right here, and we're gonna react it with HBr. Okay. So HBr is a very strong acid. That means that it's gonna look for the most basic atom in this molecule, which is gonna be the oxygen of the alcohol, which has 2 pairs of electrons, right? And I'm gonna draw out the HBr like this, where the oxygen is gonna grab the hydrogen of the HBr using one of its pairs of electrons, right? And then the bond between the hydrogen being
breaks
off onto the bromine right there, like that, right? And that is going to give us this intermediate right here, where the oxygen now is bonded to 2 hydrogens, and it has 1 pair of electrons, which will have a formal charge of +1, like that, right? And this right here is a good leaving group, right? We converted this bad leaving group, OH, into a good leaving group, oxonium ion, with a positive charge.
So is something that's like more positive, is that a good leaving group?
Yeah, something that's more positive is going to be a good leaving group because when it leaves, it's going to leave with a pair of electrons, which will come from this bond right here, because this bond is just going to break off as a pair of electrons onto that oxygen, and then that oxygen is able to hold that extra pair of electrons because...
So just H2O.
Yeah, it's going to be H2O. It's going to be neutral H2O, and that's stable. At least that's a stable molecule, right? So we're just going to kick it out like that.
Yep.
Right? And because the carbon here lost the bond, this carbon is positively charged, and you notice how this methyl group here, I made it into a flat planar bond, like it came from a dash to a flat planar bond.
Yeah.
That's because this sp3 carbon became sp2 hybridized, which is trigonoplanar. Everything is flat and planar in sp2 hybridized carbon. There's no wedge, there's no dash.
So sp3 to sp2 becomes flat.
Yeah, sp3 is tetrahedral shape, which has 2 flat bonds and 1 wedge, 1 dash, right? Like 2 flat bonds, 1 wedge, 1 dash. But this carbon here, it only has 3 bonds, 1, 2, 3, which is trigonoplanar sp2. Everything is flat. There's no wedge, there's no dash in this sp2 carbon here.
Okay, yeah.
Right? And this is a tertiary carbocation because this carbon here is surrounded by 3 other R groups, 1, 2, 3, like that. Right? And I'm just going to draw out the leaving group that left, which is this water molecule here, right there. Okay? Okay, now we could just bring in the Br minus that got kicked out, right? Because before this Br here had 3 pairs of electrons. Now it has 4 pairs of electrons with a negative charge, and that's the nucleophile. That's gonna
positive.
Attack the positive charge, the electrophile right there, which makes that new bond right there. And you know how I said this is flat and planar right here? Yeah. The bromine could either attack the top side, making the bromine a wedge and forcing this methyl to be a dash, or it can attack on the bottom side, making the bromine a dash and forcing the methyl to become a wedge, right? So we would actually have to draw out 2 different products here. One where the bromine is wedge, forcing the methyl to become a dash, and one where the bromine is a dash, forcing the methyl to be a wedge, like that.
Okay.
Right? And these are diastereomers of each other because you notice how the chiral center in red, which I'm starring, is different, right? Like one is going to be R, one is going to be S.
Yeah.
Chemistry. The one in blue right here is going to stay the exact same, right? And if you remember back to stereoisomers, diastereomers are when some chiral centers change, some chiral centers stay the same, right? The one that's changing is the red chiral center. The one that's staying the same is the blue chiral center right there.
Okay.
Right. If that chiral center was not there, right, you could have just drawn like this right here, and if that was a chiral center, then you could do the plus minus symbol, racemic mixture, like how Helix does in his lecture notes.
Oh, I can just write plus minus.
Right. If it's gonna be in enantiomer, right? In this case right here, we couldn't do plus minus.
Okay.
Right? Because if we did plus minus here, that means that this, like the other product, would have been this right here.
Can you show me an enantiomer again? Like, how do I know if it's an enantiomer versus
diastereomer?
Yeah.
Yeah. So let's say we have something like this, right? Where there's two chiral centers here. There's this red chiral center and there's this blue chiral center right here.
Got it.
Right. Enantiomers is when every single chiral center flips. So an enantiomer of that structure would be this right here. Right, where you notice how the red chiral center flipped and the blue chiral center flipped.
Both have to flip. Okay, got it.
Both have to flip, right? Like if there's 3 chiral centers, all 3 have to flip. If it's 4 chiral centers, all 4 have to flip for it to be considered enantiomers.
Got it.
Right, but let's say you have like 7 chiral centers in a molecule, right? A random molecule, 7 chiral centers. If 3 of them flip and 4 of them stay the same, they won't be enantiomers because not all 7 flipped.
They're gonna be diastereomer.
Yes, diastereomers, right? And there could be a lot of diastereomers because you know how like if you have 7 chiral centers, 1 can change and 6 can stay the same, right? So there's different combinations of the diastereomers there.
Okay.
Right?
How do I know when to indicate like stereochemistry? I guess.
You know that because if this important part right here of the mechanism, the carbocation intermediate, right?
Okay.
And this bromine here, when it comes in to attack that carbon right there, if you know and understand the shape of it and how it's flat, the bromine can attack on the top, giving us a wedge bromine and this a dash methyl, or it can attack on the bottom, giving us a dash bromine and a wedge methyl, right? So if this wasn't there and if this was a chiral center, right? Well, it's not a chiral center because like let's say this wasn't there right here. This group would be the same exact group as that right there, like that.
Yeah.
Right? But let's say if it was a chiral center, then you wouldn't have to draw that. You could have just done plus minus like right there because you know the other product would be flipped, like the bromine.
Because there's only one.
Yeah, there's only one chiral center, right? There's only one.
Is there always going to be stereochemistry for these kind of problems then?
Yeah, there's always going to be stereochemistry for these kind of problems, especially with the SN1, E1, SN1 stuff. E1 is about alkene, like trans alkene or something like that.
So SN1. Always. You said E1, not really?
E1, there is stereochemistry as well, and I'll give you an example of that, right? Well, it's kind of tricky, but before that, I want to give you one more example because there's a trickier example than this that we just did right here. Let's say we have something like this, and we react it with HCl. Describe to me the mechanism, like what you would do first here.
I know the lone pairs on oxygen attack, or does the lone pair attacks the hydrogen and the hydrogen breaks off from the chlorine.
Not the hydrogen. Oh, yeah, it breaks off from the chlorine, but how would it do that? Like what happens to this bond right here that has 2 electrons? Like where would the 2 electrons of this bond go to?
It goes to the left, right?
To
the
chlorine. Yep, to the chlorine. The 2 electrons in that bond are gonna go off onto that chlorine.
Yeah, they go negative. Okay, because chlorine. Okay, got it.
Yep. Okay. And what would our intermediate look like after that?
It would be like H2O instead of OH, and then you have chlorine as a negative.
And what charge would the oxygen have right here?
Positive.
Right. And would this be considered a good or bad leaving group?
Good.
Good leaving group, right. And now, once you have a good leaving group, can it leave to form a stable carbocation right away?
Kim, which part? Sorry. Yeah, there would be a carbocation formed, no?
Right. By just kicking out that leaving group by itself to form this carbocation right here, Now, what do you think is gonna happen next from here?
The chlorine's gonna attach.
So this is the tricky part here. Whenever you form a carbocation intermediate, right, you always stop and you gotta look out for something called a carbocation rearrangement. And that could be in the form of a hydride shift or methyl shift.
So the carbocation rearranges to the most tertiary.
This position right here, right? But in the mechanism, do not draw the carbocation moving there like that. Because do you know what a curved arrow represents in organic chemistry? Like
Electron.
Electrons and movement. This right here has no electrons. It's positively charged. It's missing electrons. Right? So I'm gonna draw out that invisible hydrogen right there, where this bond right here to the hydrogen is gonna move to that carbocation right there, that void right there, that empty space right there.
And then the positive charge goes on the tertiary.
Right, because this carbon here lost the bond. It lost this hydrogen bond right here. Like, if I highlight this hydrogen bond right here in yellow, that's this hydrogen bond right here in yellow, right there. That's why that carbon is now neutral, because it gained the bond, which is this bond right there.
Makes sense.
Right? Now the chlorine is able to attack the most stable position, most stable carbocation intermediate right there.
Okay, so it doesn't attack. That's the two-step, right?
That's the two-step, and the way that I drew it, we're not gonna form a chiral center, but I'm just gonna add a extra methyl group here, so then we do have a chiral center, right? So when we do that, how many products would we form from this step here? How many possible products here when the chlorine attacks this carbocation? Right.
But just be one.
It would be two, right? Because you know how this is a flat carbon? Chlorine could be a wedge, forcing the methyl to be a dash, or the other way around. But because we only have one chiral center, we could do plus minus with C mixture, like that.
Plus minus, okay.
Right. Because this is a chiral center here. There's 4 different groups attached to it.
Because it can attack front or back?
Yeah, it could attack front or back because of this flat sp2 carbon right there. That's very important.
Only one chiral. Okay, got it. So only one chiral. Got it.
Only one chiral center right here. And then if there was another chiral center, we couldn't do that. Like we have to draw out the other product.
You have to do the two. Okay, got it.
Yeah. Right. Nice. Okay, so that's SN1. Let me show you an example with a E1 reaction here. Okay. So let's say we have something like this.
Benzene.
Okay. OH. And this time, let's do h2so4 and heat. Okay. So now h2so4, I'm going to draw out in this form for the mechanism. What do you think is going to happen in the very first step? It's the same exact very first step as we did previously.
Electrons from the oxygen attack the hydrogen from h2so4.
Right. And what will the 2 electrons in this bond between the H being grabbed and this leaving group do? Like, where would the electrons here go?
Go to the right, and then you have H2O4 minus.
Yes. Minus. Correct. And we're going to form the same intermediate, the oxonium ion, the OH2+, which is a good leaving group. And once we have that good leaving group, we can kick it off, form the carbocation intermediate, which is going to be initially... secondary carbocation, like that, and then we have water there. Now, the thing that we kicked out, h2so4 minus, right? It's not a nucleophile because this negative charge here is very stable. Like if you draw out the Lewis structure of it, you notice that this negative charge here can do resonance with that structure, right? And more resonance means more stable, more stability. It's very happy. Very stable, so that means that it's not going to react. It's going to be less reactive. It's a weak nucleophile, right? So it can't attack that electrophile because it's very weak. Okay, but let's do a hydride shift to form the more stable carbocation intermediate, which is going to be tertiary here. Now, once we have this right here, we can now do an elimination reaction, right? Let's call this the alpha carbon, which is the carbocation carbon. And locate the beta carbons that has a beta hydrogen. So this is a beta carbon with a beta hydrogen. This is a beta carbon with a beta hydrogen. Which double bond do you think is going to be more stable? Do you think this double bond is going to be more stable here, or this double bond is going to be more stable here?
Well, you don't want double bond to be primary, so you want to take it from the other one on top, correct?
Yeah, this one right here at the bottom is not primary. It's gonna be di-substituted, right? Because if it was down here, there's one group here and another group there, so that's 2 groups. right there.
Mhm.
That's Gemino, right? So it would be the one on the top. So that means that this one here is gonna grab this hydrogen. This bond here is gonna make a double bond right here between the beta carbon that we grabbed, like the hydrogen we grabbed from, and the carbocation right there,
Mhm.
right? And that's gonna form a double bond right there, like that, for E1.
It's h2so4 minus the hydrogen is grabbing. Okay, so h2so4 minus grabs the hydrogen, and then the
Bond.
bond forms a double bond.
Yep, the bond here goes to make a double bond here.
Got it.
Right, which is this bond right here. Yeah.
Okay, makes sense.
Yes, nice. Okay. Okay. Any other questions, Trinity?
Honestly, I don't think so. I think we had a note card for our exam, so I feel like I already put the chart down on my like little cheat sheet thing.
Oh
so
yeah, was it similar to this? Because like I kind of just made this on the spot. I want to like make sure like this is the right one, but
it's pretty much all the same. Yeah, it's
Right,
h2so4 heat. It's halogen, or so it's all the same. So I just get confused between the SN2, SN1, but
right, and understanding the mechanism behind it, right? Like why the arrow goes there and like the shape of things, and
yeah, you
just
made it
understanding the concept.
You made it make sense too, because I was doing like other mechanisms, because
Mm-hmm.
the other mechanisms, so there's like aromatic nitration, something like that. I wrote those all down, so I feel like I kind of like understand those a little bit too. But yeah, I'll probably join in tomorrow and then ask you more questions if I have them.
That's great. That's great. And tomorrow I'll like prep problems like similar to this if you want to for your quiz on Monday, the alcohol ones.
Please,
Right?
yeah, that'd be great.
Yep, of course.
Thank you.
Yep, of course, Unity. See ya tomorrow.
I'll see you. Thank you so much.
Of course. Hey, Alicia.
Oh my god. I'll show you.
Dang. That was your favorite reaction, huh? The ozonolysis? Like cutting it? Wow.
Yeah, that was my cheat sheet. And so I'm like I can refer to these if I'm like completely lost on like a mechanism you bring up.
Right. Dang. That's crazy. You spent like a long time on that too. I remember like you wrote it down on the whiteboard and you took a picture of it, you sent it to me. I was like, you put in a lot of work into this, Alicia.
Yeah, I remember like carbocation.
Yeah, I know. Carbocation. I just talked about that too. Like right now, the carbocation like shift, like the hydride shift, and all that secondary to tertiary. Oh my gosh.
Oh, I miss when life was much simpler.
Yeah, with 118B, huh? Yeah. Okay.
Wait, I'm just sorry. I'm trying to find the files.
Yeah, of course. What's your sleep schedule been like recently?
I think yesterday I slept at like 1, but I woke up around like 7:30 or 8 o'clock.
Yeah.
But I mean, I haven't been able to wake up successfully for like my morning class, like for stats or for OChem.
Yeah,
like,
is it raining?
I kind of it was raining for the past 3 days, but it's kind of toned down a bit, and next week's supposed to be like more chill. Oh wait, so she uploaded the like her summer session 1 practice. I'm trying to see. I don't think she posted any other practice midterm. Like that's the only midterm 1 that she gave us, which was for the summer.
Yeah, we could go through that if you don't have any other questions, or like we could go over reactions like from midterm 1 if you want to. Like I could give you a big overview of things.
Okay, yeah, maybe an overview of things would be great.
An overview of things, okay.
I feel like because I don't feel like I'm like prepared to try a midterm.
To try out the midterm, yeah. Let's do that. Here, let me look through. Because my sister took Leavens with 118C, and she took notes for midterm 1, 2, and the final. So I'll look through those here.
Oh, okay, thank you.
Yeah. We went over the 2 methods of how to create a carboxylic acid with the extra carbon, right? Which is the organometallic granular agent and the hydrolysis of a nitrile route. Now let's see here. Main mechanism of carboxylic acid and derivatives, nucleophilic acyl substitution. Yep. Two extreme variations: basic conditions, acidic conditions, hydrolyze. Okay. So a very common reaction mechanism that you're gonna see in chapters 19 and 20 is going to be nucleophilic acyl substitution. Right? And to give an example of that, like a general example of that, let's say we have this carbonyl here, which is an acyl group, a carbon double bond oxygen attached to some leaving group. And this leaving group is going to be most likely attached to like a electronegative atom, like a halogen, oxygen, or nitrogen. We can add some nucleophile, which is going to be abbreviated as Nu, and we could do something called addition, where we add the nucleophile to the molecule that we have here. Right? And let's say the nucleophile here attacks the carbonyl carbon, pushes the double bond onto the oxygen. What charge would this oxygen have if we have a nucleophile attacking this carbon and this double bond here pushes onto that oxygen right there? What charge would that oxygen have?
Wasn't it be a negative?
A negative charge, right? But let's just say, like, to save time here, and because we're going over the general mechanism, that negative charge will get protonated to become the neutral OH, neutral alcohol, like that, right? Now, does this make sense so far on how we did the addition here, like to get this nucleophile onto this pink carbonyl carbon right there?
Yeah.
Right. This right here is the new bond, right? This bond here is part of the double bond, but one of the other bonds came onto the oxygen, which is now here. Okay. Now, what we could do now is we could do something called elimination, where we get rid of the old group, which is this leaving group right here. So when we do that, think of it as this oxygen here uses one of its pairs of electrons to go down to form a double bond and kicks out that leaving group right there.
Right.
Which is going to give us this structure here, where you notice how basically what we did here overall was that we substituted this leaving group with this nucleophile. That's the whole point of nucleophilic acyl substitution right there. Right. This right here in the middle is going to be called the tetrahedral intermediate. Right? And think of it as this carbon here is going to be bonded to like a lot of electronegative atoms. Like it's going to be bonded to this oxygen, whatever this nucleophile is, most likely an electronegative atom, and whatever this leaving group is, which is most likely an electronegative atom. It's very unstable. Very, very unstable. It's going to collapse. And it collapsed by forming the carbonyl and kicking out a leaving group, like that. Okay? Now, this right here can happen in two conditions. It can happen in acidic conditions, or it can happen in basic conditions. Let's go over an example of acidic conditions first. Okay? So, let's say we have a carbonyl with some leaving group, and then we have some nucleophile that's most likely going to be attached to some hydrogen, like examples of this would be like H2O, ROH, or RNH2, right? A lot of these will have a hydrogen attached to whatever the nucleophile is, like right there, right? And let's say we have some kind of acid like h2so4 attached to it. If this is neutral, would that be a weak or strong nucleophile? If this nucleophile here is neutral?
I think it would be weak.
Yep, it would be weak because there's no full negative charge. So if this is a weak nucleophile, and this carbonyl carbon here is a weak electrophile, they can't interact with each other. Like that weak nucleophile is not strong enough to attack that weak electrophile right there.
Right.
Right. So that's where the acid comes in to catalyze the reaction. That's why we call this the acid catalyst, because it catalyzes the reaction. Right. So it's gonna look for the most basic atom, which is gonna be this carbonyl oxygen right here. So the hydrogen of the h2so4 is going to be grabbed by the carbonyl oxygen to give us this protonated carbonyl right here. Where once we did that, right, this carbon here like is now activated, right? Before it had a partial positive charge, but now it has an even bigger partial positive charge. Right? And that's because this oxygen here is very positively charged, it's very angry, right? So it's gonna want to like steal the carbon's electrons even more to become neutral again, to become stable again. And when this carbon here is losing electrons, it's gonna become bigger positive charge, which is a very strong electrophile, allowing for this nucleophile here to attack that carbonyl, push the double bond onto the oxygen, and give us this tetrahedral intermediate right here. Okay, and then most likely this nucleophile here, whatever it is going to be positively charged like that. And I'll give you a like more concrete example, but this is just a brief overview, a general overview of what was common here. Okay. Now a lot of these. Yep.
Yeah. Just to go back. Just to make sure. So. For the first part, the electrons are grabbing the hydrogen, then it creates an OH, which is a greater positive charge.
Because
and then
this oxygen here, it's neutral with 2 bonds and 2 pairs of electrons, but now the new oxygen has 3 bonds, 1, 2, 3, and 1 pair of electrons, which makes it positively charged. Right. Yeah.
Okay, and then the nucleophile is then able to like attack that spot.
Attack the spot right here. Correct.
Right. Okay, that makes sense.
Yep. And then when that happens, right? This right here is the new bond, which came from the pair of electrons on the nucleophile, which is right there, right? And then this bond right here neutralizes the positively charged oxygen, because you see how this oxygen is now neutral. It's now neutral because it gained a pair of electrons, which is gonna come from this bond right there, like that. Right? Okay. Now, once you get this tetrahedral intermediate right here, a lot of these are gonna follow like these 2 patterns here. We are going to deprotonate the group that you want to keep, and then you are going to protonate the group that you want to kick out, right? Because if you think about it, when you deprotonate something, you make it have 1 less charge. Like if you deprotonate something positive, you make it neutral, right? And that makes it into a bad leaving group. If you protonate something like a water molecule and it becomes like positively charged, that makes it into a good leaving group. And then that's good for us because we want to kick that group out, right? And in these mechanisms, we want to kick out the old group and we want to keep the new group, depending on the question, right? So if you look at this right here, which one of these looks like the good leaving group? This, or this? Let's say this is A, this is B, this is C. Which one of these looks like the good leaving group?
I want to say C, because we said that.
Yeah. So based on the charge, right? Like OH here is neutral, this is neutral, and then this NuH here is positively charged. Based on the charge, which one looks like the better leaving group? This based on the charge.
I think the NuH.
Yeah, the NuH, because when it leaves, it's gonna leave as a neutral molecule. If we kick out the OH or Lg as it is right now, it's gonna leave it with a negative charge like that. right? And then if we kick out the NUH, it's going to be neutral. And then this NUH here is going to be more stable than these negative charge leaving groups right there, like that, right? But that's not good because if we kick it out, right? Like let's say we reform a carbonyl and we kick out the good leaving group as it is right now, we're gonna go backward, right? Like we're gonna go back to what we started with, and we don't want that, right? To get something new, we're gonna have to make this into a bad leaving group, and to make this into a bad leaving group, we have to make it neutral, and to make it neutral, we're gonna deprotonate it using the h2so4 minus that we created in the first step. Like this h2so4 minus here will come from here in the first step of the mechanism, right? Like, you know how the carbonyl oxygen grabbed the H and then the bond between the H and oxygen goes onto that oxygen right there? That gives us oxygen negative charge, which is the base that we're going to use to deprotonate this nucleophile and give that nucleophile a neutral charge now, because it will gain a pair of electrons from this bond right here. Right.
Could you explain that one more time?
Yeah, of course. So, does the very first step of the mechanism make sense on how we got these two arrows here? Yeah. The oxygen here will bond with this hydrogen by using this pink pair of electrons right here, right? And this bond right here between the oxygen and hydrogen is gonna break off and go onto this oxygen, giving that oxygen a negative charge. So as a result, we're gonna have this floating around somewhere in the solution, this h2so4 minus molecule, right? And then does this make sense so far, this next step of the mechanism?
Yeah.
Right. Now once we get this tetrahedral intermediate right here, we want to make this positively charged nucleophile neutral, right? And to do that, we have to give it a pair of electrons, or we have to deprotonate it. Like, you notice how we have a proton here to deprotonate?
Yeah.
This h2so4 minus here that we created in the very first step is gonna come around and use its pair of electrons, one of its pairs of electrons, to grab this proton here.
Okay,
to grab that hydrogen right there, right? And as that hydrogen is being grabbed, the bond between the hydrogen being grabbed and nucleophile, those two electrons in that bond are gonna go onto the nucleophile right there. Right? And that's gonna make that nucleophile gain the pair of electrons and become neutral, like this. Right? This nucleophile no longer has its proton because it was grabbed by the h2so4 minus. So that's why we have this h2so4 again, like that.
Okay, that makes sense.
Yep. Now this is a neutral tetrahedral intermediate. This leaving group right here is gonna, like, we want it to be a good leaving group because we want to kick it out. Like, that's the old group, we want to kick it out. Right now it's a bad leaving group. To make it into a good leaving group, we have to protonate it, right? Protonate the group that you want to kick out to convert it into a good leaving group. If we want this to have a positive charge, we're gonna have to make it gain a bond. And to make it gain a bond, it's gonna grab this proton here from the h2so4, and then that's gonna kick out another h2so4 minus right there, like that.
Okay.
Right. Okay. Now,
so in a way, it's kind of like picking up hydrogens and then having them leave, and then like we're basically using the OSO3H.
We're gonna
steps.
Yeah, use the h2so4 and h2so4 minus, or the OSO3H, in multiple steps of the mechanism, right? That's the acid catalyst being like protonated and deprotonated like multiple times throughout the mechanism.
Okay.
Right.
That makes sense.
Yep. Now you see how here this is the good leaving group. That's now perfect because that's the group that we want to kick out in the first place. So we're gonna use one of the pairs of electrons on this oxygen right here to go down and form a carbonyl or a carbon number 1 oxygen and kick out that good leaving group right there, like that. Right? Like, this bond here is gonna break off as a pair of electrons, like, because there's 2 electrons in there, and go onto that leaving group right there. And what charge would this leaving group have if, like, we break off that leaving group and give it a pair of electrons? Like what
Wouldn't
would
it
be?
make it neutral?
Yep, it would be neutral. Correct. What charge would this oxygen here be? Now.
It would. Wouldn't it be a positive?
Yep, it would be a positive charge. I'm just drawing this out
Is
because
it, yeah.
this is the leaving group. It's not neutral. This oxygen here with 3 bonds, 1, 2, 3, and 1 pair of electrons is going to be positively charged like that. Right? Now we almost have our final answer. Right? What was formed here? Like what gets formed here? After we protonate the leaving group, what gets kicked out in the h2so4 molecule?
It would it just be the hydrogen?
So the leaving group here grab this hydrogen, which is this hydrogen right here. What happened to this part of the molecule here? What did that become?
It would be OSO3H.
With what charge? What charge?
It would be positive.
So this oxygen here is neutral, right? With 2 pairs of electrons. We're gonna give this oxygen another pair of electrons from this bond right here, because you know how when this leaving group grabs the hydrogen,
it would be negative then.
Yep, it would be negative charge because that oxygen now will be having
like a pair of electrons.
Yeah.
It would be a lot.
Yeah, it would be negatively charged, which is the base, right? And that base is going to how would we neutralize this positive charge oxygen right here? Like,
it would grab the hydrogen.
Yep, this h2so3 minus here would grab the hydrogen, and what happens to this bond between the hydrogen being grabbed and positively charged oxygen?
It would give it a pair of electrons to the oxygen.
Yep, like that, and that makes the oxygen.
So it becomes neutral.
Yes, it becomes neutral, like that. And what did we reform here? Like what does this h2so3 minus become?
It would be an h2so4.
Yes, and that's why we call this an acid catalyst, because it gets reformed in the mechanism.
Right? Oh,
it gets used up multiple times, right? The biggest thing here is that we saw that we substituted this Lg leaving group with this Nu nucleophile right there, right? Okay, that's acidic conditions, which is longer than basic conditions. Now we could go back to this general mechanism, but I want to give you a more concrete example here. Let's say we have this carboxylic acid, right? And I give you this alcohol with h2so4, right? This right here would be the Nu, the nucleophile. This right here would be the Lg, the leaving group, right? Can you describe to me step by step how you would do the mechanism here?
So would we first use the... Wait, let me count real quick.
Yep.
I wanted to say we have to create the h2so4 to be a positively charged.
So we want to create a positive charge on which of these oxygens? This oxygen or this oxygen right here?
The double bond.
Yeah, the double bond oxygen is the more basic one, which is gonna react with this very strong acid here, h2so4. So this double bond oxygen is gonna grab that H from the h2so4. That bond is gonna go off and go kick off that h2so3 minus and give us this intermediate right here. Right, that step right there is the activation step in acidic conditions, right? Because this right here is a weak electrophile with a partial positive charge, but once we get this carbonyl oxygen protonated, this carbonyl carbon is now having a bigger positive charge, right? It's now a stronger electrophile. Now what do you think happens next? What can attack this strong activated carbonyl carbon electrophile now?
I think wouldn't it be the OSO3H?
OSO3H. So the OSO3H here does have a negative charge, right, on the oxygen. But this negative charge here, you know how it could do resonance 2 times with the structure like that?
Mm-hmm.
That resonance right there, do you think it would increase or decrease the stability of the molecule?
It would decrease.
So more resonance means more stability.
Stability.
Right. Because think of it as like if the electrons can move more, it's gonna be more happy, like more stable.
Yeah.
If the electrons can move more, so if it's more stable, it's gonna be less reactive, right?
Okay.
So that means that it's gonna be a weak nucleophile, right? So we won't use this h2so4 minus as the nucleophile. We're gonna use this.
Oh, we'd use the other one.
This alcohol right here, the with 2 pairs of electrons as the nucleophile, right? Okay, so we're gonna use this alcohol to attack this carbon. What other arrow has to happen when we do this attack? Like that's the first arrow. What's the other arrow?
The one to the double bond to the O.
Yep, like that, and that's gonna form what kind of intermediate? Like what's the name of the intermediate?
Tetrahedral?
Yep, tetrahedral. Yep, and be careful of that word because that could show up on Liebman's vocab section, right? It's gonna be OH here. It's gonna be this oxygen here, right? Is the oxygen right here, right? And what else is attached to this oxygen here? Like what is attached to that oxygen that you see?
The is that a propyl?
Isopropyl.
Isopropyl, yeah.
Right. Isopropyl group and
the hydrogen.
Yep, the hydrogen. So what charge would this oxygen have?
A positive.
Positive charge, right? So now this is our tetrahedral intermediate. This is the new group that we just added, and that's the group that we want to keep. And we want to get rid of one of these old leaving groups, like the OH right there. How can we convert this into a bad leaving group so then we can keep it in the molecule? How can we get rid of this positive charge there?
I think the OSO. I want to say the OSO3H. I don't know.
Yep, OSO3H or HSO3 minus, right?
Yeah.
We'll deprotonate it and make it neutral. Right.
Okay, grab it. Yeah, hydrogen.
Yep, that's correct. Now, how can we make this positive after that step? Like imagine we did that already, and this is now neutral, and we want to make this positive now. How can we make this positive if we have a h2so4 floating around? Because we want to make this into a good leaving group, but for it to be a good leaving group, we have to make it positive charge. And how can we make this positive charge in acidic conditions here?
I'm kind of stuck.
That's okay. We want to protonate it. We want to give it an extra bond. So we could do that by giving it a bond to a hydrogen in acidic conditions, like that, right? Because you know how oxygen with 3 bonds is positively charged? If we protonated it and give that oxygen an extra hydrogen right there, that oxygen would be positively charged, making this a good leaving group right here.
Oh, okay.
Right?
I see what you mean.
But you know how we did that in 2 steps? Like we deprotonated it first to make it neutral, and then we protonated this after to make it positively charged?
Yeah.
We could do that at the same step by deprotonating this group and protonating this group at the same time like that. Some professors allow it in some schools, some professors don't allow it. Liebman's will allow this in the mechanism right here.
Yeah, I think that's what she was doing in lecture.
Yeah, that saves time on the exam as well, right?
Oh, okay.
Because this oxygen here will grab this hydrogen, making another bond, making it positively charged, whereas this oxygen here is going to lose that hydrogen, making it neutral. And that saves it like a step that you have to draw in the mechanism. Right?
So instead of having the OSO3H grab the hydrogen, we'll have that one grab it. It's instead.
Yeah, right. Because that one's gonna have to grab a hydrogen anyway, right? So we could kill two birds with one stone here doing that step. Right. Now, once everything is in place, we can reform the carbonyl, kick out that good leaving group that we just formed, and form this intermediate right here. Oxygen, positive charge. That's the leaving group that's now neutral. Water left. Now the very final step here, what do you think the very final step is to make this neutral here?
I think we would want it to get rid of the hydrogen.
Yeah, we want to get rid of this hydrogen. And what can we use to get rid of that hydrogen?
The OSO3H.
Yeah, the OSO3H minus is going to act as a base, grab the hydrogen. The bond between the hydrogen being grabbed and oxygen right there represents 2 electrons. Those 2 electrons are going to go onto that positively charged oxygen to make it neutral, like this. Right, and then we reform our acid catalyst h2so4, giving us our final ester.
So since you were explaining the part where we can kill 2 birds with 1 stone by having the one of the oxygens take the hydrogen from the other bond.
Yep.
Because we were using it in that case, let's say we were to use the OSO3H, would we would that mean that we're using like not to say there's an excess floating around, but are we thinking that we're using the same exact like h2so4 all throughout, like the singular, or like, do you know what I mean?
Yeah, I know what you mean. Like when OSO3H minus grabs this hydrogen and it becomes h2so4, which that h2so4
imagine if we were to do that instead.
Could be used. Like it could be the same h2so4 and OSO3H being reused and recycled throughout the mechanism, right? But there's gonna be excess amount of h2so4 in the solution. Like there's not gonna be only one molecule of h2so4. There's gonna be many other h2so4 floating around the solution like that, right? But that many h2so4 floating around in the solution is gonna accommodate for many of these intermediates in the solution as well. So they're gonna pair off with like other intermediates like that.
Okay, that makes sense. Right. Because I was like kind of wondering how like in my head I was thinking that the h2so4 would reform like a step earlier.
Right. And
like kind of.
Yeah, I get what you mean. Like if there's only one HSO4 minus and if there's not enough to react to this intermediate, like there would be no reaction, something like that. Yeah. That is a good question, because like we're zooming in onto only like one reaction out of the solution. Like keep in mind that this is a lot in the solution as well, right? This is also excess, which is gonna react with the excess amount of h2so4, right? Yeah, that's a good question. That's a good question, Elysia. Yeah.
Okay. Thank you.
Of course. And this is the final product here, and you notice how we substituted the leaving group, which is the OH here in the original reactant, with the nucleophile, just minus 1 hydrogen. Like this is the nucleophile right here. Like the hydrogen is no longer there, right there, right? This is a carboxylic acid. What is this functional group right here? A carbonyl with an OR group.
Oh, okay, I see it. So it would be an ester.
An ester, yes. And if you have a carboxylic acid converting into an ester with an alcohol and acidic conditions, that is going to be called Fischer Esterification.
Esterification?
Yeah. Esterification. Right? Because we're creating an ester from a carboxylic acid in acidic conditions with alcohol. Right? Fischer esterification can never work in basic conditions. Can you think of why it can never work in basic conditions? Think about what functional group is present here.
Wouldn't it be the OH?
This is a carboxylic acid, which is an acid, right? If you try to add base, what would that acid do?
Oh, it's gonna want to attack. It's gonna want to attack the OH, not the carbonyl.
Yes, it's gonna want to deproteinate the OH instead of attacking the carbonyl, like that. That's why Fischer esterification can only work in acidic conditions, right? So if you see this reacting with a base and its solvent, then you're just gonna deproteinate that carboxylic acid to get the carboxylate ion. That's the final answer.
Oh, okay. Okay, that makes sense. Thank you.
Yep, of course, Elisa. Tomorrow, we'll go over the basic conditions and more examples of this nucleophilic acyl substitution. But I just gave you one specific example here in acidic conditions, which is Fischer esterification. Later on, we could go over trans esterification. Right?
Okay.
Trans esterification, of course.
Yay.
Yeah.
Thank you so much. And I was wondering if I could possibly get the notes for that as well.
Yeah, the notes for this will be uploaded to the school. Like, you know how I categorize it, like through quarter by quarter, week by week. It's gonna be uploaded to that school as well.
Oh, okay, nice.
Yeah.
You know, I've been watching your videos and I've been like liking the ones I watch. So if you see me,
oh yeah, thank you.
Like likes, that's because I'm studying through your past videos.
The past videos, like I see on my YouTube analytics, like there's views on like previous videos, but they don't tell me who. So like I was like, oh shoot, someone's been watching my old videos. I know.
That could be me.
But I saw you comment on the final in-person review session. I loved it. I love that comment.
Yeah. Oh yeah. Oh my gosh. I love that you come out this way to do this.
Yes.
So nice.
I enjoy it. I really do. Like it's like so satisfying and like fulfilling for me, you know?
Yeah. I mean, do you like what part do you like about it? Like
I like visiting campus again, seeing students there, talking to them, and like just like tutoring them and making them understand the material better as well.
Yeah. I know the way you put things are like it's so good. It's like, you know, I was telling my friends, I'm like, I wish, I mean, I feel like professors are starting to pick up on like some of the phrases that we say. Like so like they use our lingo and sometimes like they're able to teach a lesson with our lingo. So it's like it feels nice, but it's like, you know, like sometimes it's like pretty rare to find those professors who go with like today's
like lingo,
how
like
we communicate. Because sometimes professors teach in the way that, you know, they were raised from other professors, but it's like it's not traditional, but it's just like how they learned.
Right. And also like I've been noticing that as well. Like recently, like Helix, Levens, and like Parahat, like they've been using like phrases that we usually learn from. So that's good. That they're catching on.
I know. I mean, I know Enderly was way ahead of our time. So like he you know, he grabbed all of our attention before.
Yeah, he's
nice,
really good. Yeah.
But I'm like, it makes me curious. Like I always think about, like, you know, once those professors, like, you know, they retire and whatever, and we were having like a new set of like professors, like basically like us becoming like those professors. It's like, are we gonna be teaching, like, you know, are we gonna teach like how they taught us, or are we gonna like, you know, talk using our own lingo? Because
I know,
kind of, you know, our world is like changing so much.
Is like so rapidly too, especially with the new tech and AI coming out, and like all the memes too from TikTok and Instagram. those different phrases. Like I don't even like I can't catch up anymore. Like there's like something called 6-7. I don't know what that means.
Oh yes,
I keep hearing that
my
around.
yeah, my professor
Yeah.
for stats, he was like, oh, 6-7,
Yeah,
and I'm like, oh
yeah,
my
yeah. Six,
goodness, like,
seven.
and then everyone's like cackling and stuff, like they're like, oh
Yeah.
yeah, but like he's also a dad, so like he hears the lingo from
Mhm.
his
Your
kids,
kids,
so like
yeah.
it makes sense. But
Uh-huh.
you know, there's like I like how TikTok like
Yeah.
there's like some kids who are like explaining it like how we would understand it. So like
Uh-huh.
people like you know, like you
Mhm.
guys are like getting on social media and like explaining things in like in a way that you know like we understand. It doesn't seem like
Uh-huh.
you're reading off of a textbook.
Right, right.
And you know, I'm even getting like
Yeah.
TikTok like what's it called? OChem edits and bio
Uh-huh.
edits and
Oh
stuff
yeah,
like with the
yeah.
music in the background and stuff and I'm like, "Oh my gosh, I
Uh,
love it so much."
yes, yes.
Yeah, sometimes I just try to like find ways to
What you're
enjoy the
learning.
classes. Yeah, because
Yeah.
sometimes I lose I lose
Mm-hmm.
sight of like why I'm here and
Mm-hmm.
stuff because like all the material is hard, but like
It
once I find a
is.
way to make it seem like it's fun, you know,
Mm-hmm.
makes me just want to keep learning
Mm-hmm. Yes, great. Yeah, and
stuff.
it's like if you tell a story, like make memes and like make yourself laugh with the material, it's gonna stick more. Like.
Yeah. I know, and then like you know like um my friend she was like talking to me about amoeboid riz and stuff like how amoebas like react and like they join into one
Uh-huh.
or something like that
Oh
and like
yeah.
I was like oh my gosh wait you're so right. I'm like I would
Yeah.
have never thought of amoebas to
Oh,
be like that.
that's so funny.
I
That's
don't
so
know if you know what I
funny.
mean. Like
Mead
I'm in
borders like they
BizCC.
combine and stuff like
Yeah.
that.
And they're like stuck with each other forever.
Oh my gosh. Well, that's a good way to,
Yeah.
to remember it too. Like with that
I know.
Riz, that's funny.
I know. It's and honestly, like I'm like really happy that I'm like learning to
Mhm.
like talk to people in my classes because before I was really like I wouldn't
Shy,
really make much.
introverted.
Yeah, I was shy and
Yeah.
I wouldn't make much of the effort to talk to
Mm-hmm.
people just because like I'm not really not that social, but
Mm-hmm.
you know, the two people that I sit with in that class, like they approached me and they talked to me and it
Uh-huh.
feels nice to talk to people and like help each other explain
Mm-hmm.
things in that
It
way or
is.
like kind of make it fun.
Mm-hmm. Right. And
So,
like if you teach it like to them, like that's a good way to know like test yourself and like to really know if you know the material and like that's a good way of studying as well, teaching it to other people, you know?
yeah, I know. I like it a lot and
Mm-hmm.
so like it's not too bad.
Mm-hmm.
I know
Yeah.
in the summer I took Biz 2A with
Uh-huh.
Usman.
Mm.
He's like I think he was like a head TA before, but he was teaching it over the summer. And
Mm-hmm.
he taught things like really well.
Mm-hmm.
And like even though the pace was like really fast,
Mm-hmm.
I was able to catch up and I actually got like one of my it sounds so embarrassing because I'm in my third
Mm-hmm.
year and like I'm
Mm-hmm.
saying I'm getting my like one of my first
Yeah.
A's in STEM classes,
Uh-huh. Uh-huh.
but I feel like there's been improvement in like
Mm-hmm.
catching up with like how fast classes go and stuff.
Right.
So
Mm-hmm.
I don't know, maybe I'm being super bold this quarter taking
Mm-hmm.
3 stems.
Three stems. I know
But
that
I'm
is a
like
lot.
yeah, I'm trying to be like I'm very hopeful
Mm-hmm.
and just trying to like stay positive through it all.
Mm-hmm. Right, right. That's good. And like it's still early in the quarter, so like that's good that you're putting in the work now. Like I see you like studying, like it's good. Have you been using the Forest app, Elysia?
Wait, what?
Have you been using the
Oh,
Forest app?
oh yeah.
Yeah.
I've been trying to, but like
Mm-hmm.
because I've been like not going to my OChem lecture, I
Yeah.
try not to count it as me studying. Like
Mm-hmm. Mm-hmm.
like cause the forest app I kind of use
Mm-hmm.
to like study for the most of the time to catch or like to really monitor how much I'm studying toward each subject, but it's like I'm like just taking notes right now.
Right. Taking those. Yeah. I
Yeah.
see. That's good.
Today
Oh.
I popped my first energy drink
Oh, you popped
of
your
the
first energy drink?
quarter.
Like first ever? Oh, in
Uh,
October. Dang. I
I
remember last time
know.
you had like Celsius is like a lot of Celsius. Oh my gosh.
Yes, I
Uh,
was addicted. It was a very bad habit of
yeah,
mine. I've been
I
trying
know.
to
Uh-huh.
start this quarter with healthier
Yeah.
habits.
Me too. Me too. You
Um,
know, Alicia, like
yeah.
the beginning of the
Oh,
quarter, like I was like, I'm not gonna do energy drinks anymore. But today I was so tired, I couldn't do it anymore. I went to
uh,
the cafe and I got a Celsius today.
oh my gosh,
Oh
you're
my
the
gosh.
goat.
Dang, welcome
I
to the club. Welcome to
know.
the club.
I know. I'm just hoping that
uh,
it doesn't get worse from here,
yeah, I
'cause
know.
my routine, I've noticed I think starting over the summer, how
Mm-hmm.
much coffee helps start your day.
Mm-hmm.
Like it's like that booster that you need so that you're not like starting your morning like groggy and like slow, and it just
Mm-hmm.
gives you that energy and it helps like at least last until like the late evening.
Yeah, hey, the coffee, like not energy drink, but like caffeine.
Uh-huh.
Yeah, yeah. Have you like been like leaning towards coffee more than energy drinks?
Yeah, I mean,
Mm-hmm.
my routine in the morning is at least when I wake up,
Mm-hmm.
I drink a coffee right away, and
Mm-hmm.
I make myself like an iced coffee with like
Mm-hmm.
the cold brew I have and like a
Mm-hmm.
creamer, and
Mm-hmm.
it's easy and like
Mm-hmm.
very simple, and like I'm in my apartment so I can have
Mm-hmm.
ice and stuff. Like it's
Dang.
really nice. Like no more
Yeah.
dorm life.
Dang. That sounds so like easy, simple, and cozy, especially during the raining season.
Yes, I know. It
Uh,
actually feels like less depressing.
mm-hmm.
Like surprisingly, it feels like
Mm-hmm.
I have a home here in Davis in a way.
Yeah. Uh-huh.
Like
Yeah.
I have like a little bit
Mm-hmm.
more space to like move around more, a little bit more privacy.
Right. Do you have your own room or like you have a roommate?
I share with
Mm-hmm.
my roommate I had from last year,
Mm-hmm. Mm-hmm.
but it was yeah, there was three of us actually and a cat.
Oh, wow.
It was it was a little bit cramped, but I'm
Mm.
like very happy
Mm-hmm.
to be in my apartment now.
Yeah, yeah. Enjoy it because like I'm thinking back at it, I kind of miss my Davis apartment because I think like you've seen my Davis apartment before, like look the background and stuff like that.
Oh, yeah.
Yeah,
Where
like in
did you
office
stay?
hours. A Sequoia apartment, like by North
Oh, wait,
Davis.
wait. Is that yeah, yeah. Isn't that by Umiti and
Yeah, it is. It is.
oh,
MBT,
yeah,
it's a
I've been in that
Safeway.
area.
Yeah.
Yeah. Wait, what was the
Dang.
grocery store there? Is it a Safeway or
Safeway. It's the Safeway.
okay, got it.
Yeah, it was
Yeah,
walking
it's a
distance from
Safeway.
there. Yeah, it's a J and G
I
line.
know.
For the Unitrans, it's a J and G line.
Oh, wait, so then did you ever have to walk far for your for to the bus or
No,
was
no,
it
no,
like
no,
pretty
no.
easy?
It was pretty easy. It's like walking right
Ah.
outside the apartment, and it's right there.
Uh-huh. Wow. See, yeah,
Yeah.
that's like for me, surprisingly, not surprisingly, but like
Uh-huh.
I've been taking bus more often. I've
Mm-hmm.
barely ever taken my scooter
Oh
out.
yeah. Uh-huh.
Yeah, so and it feels nice because not only am I just like, having like new healthier changes to
Mm-hmm.
like prioritizing sleep or drinking
Mm-hmm.
coffee in the mornings,
Yeah.
but I'm getting like my steps in by
Mm-hmm.
taking the bus.
Yes. That's good. That's good. Like
Yeah,
I remember
'cause
like
yeah.
my mode of transport as well. Like it used to be biking, like at the beginning of Davis, like I was at Davis,
Uh-huh.
to taking the bus, right?
Mhm.
And then I eventually went to driving to the parking lots. But I
Yeah.
heard they raised the tickets, like the parking
Ooh,
permit
yeah,
like
I
tickets. I
heard.
heard, yeah, yeah. Oh my
Yeah.
gosh, they raised that like every time now.
Yeah, thankfully I bought a parking spot, so like I
Mm-hmm.
don't have to worry too much. There's like a
Mm-hmm.
little bit of a walk from my apartment,
Mm-hmm.
but like it's nice because now I have my car. I don't have to like
Mm-hmm.
fight for parking. Oh my
Yeah,
gosh. Like
yeah.
at
Yeah.
Carto, parking was so ruthless. Like
Oh, I
people were being
know.
super stingy, leaving like
Yeah.
huge gaps between them, but not enough for a car to fit.
Oh my gosh.
Oh, that's the worst part ever.
And you get mad. You get mad when that happens.
Yeah.
Oh yeah, I would too. I
Yeah,
would be mad
but
too.
and then not only that, like the
Uh-huh.
trees that they have, it releases like a lot of sticky sap.
Mm-hmm.
So
Mm-hmm.
that means like if my car would like if I were to wash my car in one day, like couple hours or the next day after, it would be covered in sap and like
Oh no.
leaves and twigs and stuff.
Oh, dang, that
Yeah.
sucks. So then you have to like clean it before you drive again.
Yeah, and then like every time I go home, like
Hmm.
my family is like, "Why is your car so dirty?" And I said, I swear I washed it.
Yeah,
It
yeah,
just didn't
yeah.
last.
Oh no.
Yeah, but like I
Yeah.
mean it's nice 'cause like now I have my car. I'm
Hmm.
actually working two jobs.
Oh, Chipotle and where else?
Okay, when you
Hmm.
come back to Davis, they
Hmm.
have like this whole not like you know where the Trader Joe's is?
Yeah, yeah.
Yeah, they opened up all like basically a whole plaza. They have like a playing area for kids, like
Oh,
a grass
what?
area. They have a Hawaiian barbecue. They have
D-
Mendocino Farms. I've never been there, but
Dang.
they have like a dumpling place.
Oh
They
yeah,
have a
is it
Nordstrom's rack
Yankee?
and
They
a
have a Nordstrom
Ulta.
rack? Oh my
Yeah.
gosh. Oh, next time I go to Davis, I gotta go there. I gotta go there.
Yeah, it looks like we're like we've escaped Cowtown for a little.
Yeah,
You
yeah.
know?
It's
Yeah, it
advancing.
feels nice.
Oh
Yeah,
my
it's
gosh.
nice. It's like low-key bougie, but yeah, I work in
Yeah.
that plaza
Uh-huh.
and you'll find me at the L&L Hawaiian barbecue.
Oh, LNL, Hawaiian barbecue. I know that. I know that.
Yeah. But I
Dang.
mean, I don't know if I have a secure spot now.
Uh-huh.
I've been training for like 2 weeks, and so
Yeah.
far has been going good. They cut
Uh-huh.
people, but not like thankfully, I
Mm-hmm.
wasn't one of those people that got
Oh,
cut, so I
nice.
stayed. It's
Yeah.
because they have 10 cashiers or like 12
Oh,
cashiers.
dang. It gets busy, huh? It gets pretty busy.
Well, no, they because they just opened up, they were looking
Yeah.
for people and they just put a lot of people in and then like really decide from there who they wanted
Yeah.
to stay or you
Yeah.
know.
Uh-huh.
And so, I was like, kind of scared because I have two labs and
Mm-hmm.
it, it it didn't really work well with the schedule because they have like a morning shift that ends until I think 3:30 or 4 o'clock, and then a 4 o'clock to close. And those are
Mm.
the only two shifts that they
Mm-hmm.
like that they have. And so let's say I were to work or if I had class at like 4 or like my class ended at 4:30, I wouldn't
Mm-hmm.
be able to have the shift because
Mm.
the shift starts at 4.
Mm. Mm-hmm. So
Yeah.
schedule conflicts as
Yeah,
well.
but
Dang.
thankfully, it's not too bad, but I
Mm-hmm.
like how not loyal they are, but like how consistent they are with the shifts. Cause at
Mm-hmm.
Chipotle, they cut my shifts.
Oh, they do?
Yes, sometimes they're like,
Oh.
Alicia, don't come in for your shifts, and I'm like expecting to make money, and like,
Oh,
I'm like, oh
shoot.
no.
Last minute too?
Yeah,
Dang.
it's so sad because they're like, oh, sorry, we're like slow today, so don't come
Uh-huh.
in. I'm like, but I was supposed to work. It's like my only hours. Like the
Yeah.
only like there's so many people on board, so it's like I really ever get like 2 to 4 hours there. And at the Hawaiian barbecue, I got
Mm-hmm.
10 hours.
Oh, wow.
Yeah.
Dang. That's good too. What the heck? Like
Yeah,
so
I'm really
consistent.
happy.
That's good. Let's go, Elysia. Like, did you get the job recently too?
Yeah, I'm hoping that I'm able to stay, but I mean, we'll see how
Yeah.
it is.
Yeah, yeah.
But I mean, let's say if I work
Mm-hmm.
when you come back, either Chipotle or
Yeah.
Hawaiian barbecue.
Yeah, you got me, Elysia. You got me when I come back
Yeah,
on
I got
Saturday.
Hawaiian barbecue, I got the discount, and
Uh-huh.
Chipotle, they've been okay, I'll be honest,
Uh-huh.
they've been a little bit stingy with like the free meals
Oh
and stuff
yeah.
like that, but like
Uh-huh.
I can still do the discount.
Okay, okay. Yeah. Dang, that's
Yeah.
good. Thank you so much.
Yeah.
Uh-huh.
But sadly there's no more honey chicken, just to keep you alarmed.
Oh, okay. No honey chicken. Oh shoot.
Yeah, they have the carne asada steak.
Mm-hmm. Dang. Okay, okay. I'm looking forward to it, Elysia. I'll text you more details and like when I'm coming and stuff like that too.
Yeah, I'm so excited.
Yeah.
Okay.
Mm-hmm.
Well,
Yeah.
thank you so much again
Mm-hmm.
for helping me with this.
Yeah, of course, Elysia. We'll finish off like the other stuff tomorrow and like the rest of office hours before your exam next week, right? I think
Okay,
next
yes,
week.
yes.
Yeah. Mm-hmm.
Yeah.
Yeah.
Thank you so much, but
of course. Good night, Alicia.
Okay, good night, Brian.
Good night.
See ya.
See ya. Bye bye.